Dear students, today we are going to talk about few more terms from the nuclei. Here you see we will talk about the famous Einstein's mass energy equivalence relation. We will also talk about the mass defect. We will talk about binding energy and binding energy per nucleon for a given nucleus. Well, this relation, the mass energy equivalence relationship, says that mass and energy are interconvertible, means mass can convert into equivalent amount of energy under certain physical conditions provided for it, and the converse is also true. And for that, Einstein was first person to give the relation, which is named after him. E is equal to delta mc square, where E is the energy produced when delta m mass is converted into energy. The energy produced will be equal to the product of the mass in kg multiplied by the square of the speed of light in vacuum. And so if we find the value of mass which is having one atomic unit mass, that is equal to 1.66 into 10 power minus 27 kg, when this much mass is converted into energy, we use this relation to find it, and we get that the energy produced due to conversion of this much mass into energy is equal to 1.66 into 10 power minus 27 kg multiplied by 3 into 10 power 8 to the power 2, and certainly m square meter square per second square, and that becomes equal to 1.4924 into 10 power minus 10 joules. And that, when converted into mega electron volt, what we need to do is divide this expression by 1.602 into 10 power minus 19, that will convert it into electron volt, and then further divided by 10 power 6, that will convert it into mega electron volt, and that is found to be equal to 931.5 mega electron volt. That means when one atomic unit of mass, which is equal to 1.66 at 10 power minus 27 kg, is converted into energy, we get 931.5 mega electron volt of energy. And now we talk about the mass defect, the difference between the sum of the masses in free or isolated state of neutrons and protons, as much needed for forming the nucleus of an atom, and the mass of the nucleus of the atom, actual mass of the nucleus of the atom. The difference between these two is known as mass defect. Well, what is let me make you more clear, that if we have say for example, we consider the example of oxygen 8O16 isotope, then in this case we have 8 protons and 8 neutrons in the nucleus. So if we take 8 neutrons in isolation, and if we take 8 protons in isolation, we sum up their masses, means mass of isolated proton into 8 plus mass of isolated neutron into 8, that will give us the total sum mass of individual constituents which were responsible for formation of the nucleus of the oxygen. And when we find the difference between the mass, the sum of the mass of these two individuals with the actual mass of the nucleus of the oxygen, then the difference is there always found, and that difference is known as mass defect. Where has this mass been lost? Actually, this mass was used up for binding these nucleons in the nucleus, because you see, you can very well understand that the protons are all protons are having positive charge, so they will have repulsive force. So how they are held together due to this energy, which is called binding energy. Neutrons are also there, they are held together. Where how they are bound together? Because of this energy, and so this energy is known as binding energy. Where we take an example of oxygen, here you see, if the mass, we know the mass of the isolated proton is 1.00727 atomic unit, and mass of isolated neutron is 1.00866 atomic unit, and we also know that for this isotope 8O16, Z is equal to 8 and A is equal to 16, and also the mass of the nucleus of the oxygen is 15.99493 atomic unit found. So how we find the mass defect for oxygen nucleus? The total mass 8 into mass of the proton plus A, that is 16, minus Z, that is 8, within bracket, multiplied by mass of the neutron, and that whole added together, and further mass of the actual mass of the neutron nucleus of the atom is subtracted, and then it is found that the difference becomes equal to 0.13691 atomic unit. That means this much mass is lost. And what happened to that mass? That mass was converted into energy, which was capable of holding those nucleons in the nucleus of the atom. And so this much mass is lost in the process of formation of oxygen atom nucleus. Now we talk about binding energy of nucleus. Is the energy required to separate the constituent nucleons from its nucleus. Well, it is just you have seen that the mass defect, some mass is lost in the process of formation of nucleus. So if you separate those nucleons now once again, then the same amount of energy will be required to separate them from the nucleus, to separate them and make them independent and isolated. So that binding energy for oxygen can be calculated. Here you see binding energy is equal to we use the same relation, E is equal to delta mc square, and binding energy for oxygen 8O16 we have found that is equal to 1.13691. we have just found it, and multiplied by 1.66 into 10 power minus 27 kg, because 1 U is equal to 1.66 10 power minus 27 kg, and that mass multiplied by C square on calculation we get becomes equal to 0.1369 into 931.5 MeV. We have already calculated it, and so further we multiply it, we get equal to 127.53 MeV. So that means this much amount of energy is required to isolate all the nucleons of the nucleus of oxygen. 127.5 MeV energy will be required to do so. Here we have calculated this part, and that earlier, and that was found to be 931.5 MeV. We have just calculated it over here, you see. Here we have calculated that the equivalent energy of one atomic unit is equal to 931.5 MeV. So now we further talk about binding energy per nucleon. what is binding energy per nucleon? Means total binding energy for a given nucleus divided by number of atomic mass for that nucleus. That is known as binding energy per nucleon. It is equal to the average energy required to separate the nucleon from its nucleus for that nucleus. So binding energy is the total energy required to separate all the nucleons, and there are a number of nucleons. So binding energy per nucleon will be binding energy, total binding energy for a given nucleus divided by total number of nucleons present in the nucleus. That is the average energy required to pull one nucleon of the nucleus of the atom, from the nucleus of the atom. To pull one nucleon from the nucleus of the atom. So I hope that binding energy per nucleon is clear. It is actually the average energy required to separate one nucleon from the nucleus of a given atom. Binding energy, if binding energy per nucleon is having higher value, the nucleus will be more stable. If it is having lower value, the nucleus will be less stable. So that's all for today. Thank you and have a nice day.